what is the oxidation state? I don't want to know how to calculate it. I mean, if you teach somebody how to calculate it, anybody can do that without any, any chemistry knowledge, right? Anybody can just do, whether they're given the numbers, they just plug it. The same thing with formal charge. Anybody can do this calculation. It doesn't require much chemical knowledge. Just like anybody can calculate oxidation state if you give them a simple enough equation. Oxidation state is the number of lone pairs plus the number of bonding electrons minus divided by whatever. It's just a simple equation. But the situation is, if you can't go beyond that, then you don't really know anything. People are going to think you don't really know much. But you should know what it means, and this goes for all the things, all the equations. The ideal gas law. When I was taking general chem, I thought, oh great, an ideal gas law problem. Just plug in the numbers and calculate. Easy, right? Easy. But the ideal gas law is not so easy, right? Because when is it going to fail? How good is it? What kind of error do you get? That's not so easy. But to just plug in the numbers is nothing special. I don't know. The thing is, it's like this. Let's say there's knowledge. I can do the ideal gas law. Well, I'm still right at the bottom of the barrel. Don't really know anything. You can just plug in the numbers. And so this is why when you're doing these things, you want to see, you can't do it for everything because some stuff is conceptually very difficult, but if there's an opportunity to understand it a little bit deeper, you should try to do that. And so in that sense, what you say is in your own words what some of these actually give you or what they mean. And so using oxidation states, that was the emphasis earlier, but what exactly is the oxidation state in your own words? I guess it was so long ago. All that earlier stuff, there's two things that can happen. All that earlier stuff is just long gone memories, or the other thing, all that earlier stuff you've seen, you've seen it so many times because you've reviewed your notes so many times that it's ingrained into your memory. You've memorized it. All that earlier stuff. So those are the two things. When it comes to the final exam, going back, you have two ways that it's going to hit you. One, you got to review all that earlier stuff and relearn it. This is like my friend in medical school. I told you, I see this all the time. Not just him, but my friend who was applying to medical school is going to review for the MCAT. Did I tell you this? No? Yeah? He forgot everything. I think maybe I mentioned it before, but sorry to subject you again, but he forgot everything. So he was planning to take the MCAT, but there's no way he was going to be prepared because since he forgot everything, he had to relearn everything. The same thing for the final. Are you going to have to relearn everything from the beginning of the semester? It's going to take time. Do you have enough time, for the final? Or if you had it memorized, oxidation state, we covered this so much. It's the parent charge assuming what? Not the parent, it's the charge assuming what? 100% ionic. That's so critical. Assuming the bond is 100% ionic. Is it 100% ionic? No, but if it's not 100% ionic, then why are we using it? If you look at the bonds, well, the bonds vary. Bonds will vary from 0% ionic to 100% ionic. Why are we assuming all the bonds are 100%? Well, we aren't assuming all of them because it's the same thing, right? Are there any 100% ionic bonds there? No, and so this is like the next step. Once you've memorized this, then you can add some additional information to this, like this chart, and go, wait a minute. Didn't we assume all the bonds are 100% ionic in oxidation state? Yeah, we sure did. But the thing is we aren't assuming that this is correct. what we're doing is we're just leveling the playing field. That is, if we assume all the bonds are 100% ionic, and then what we do is this. We memorize how those oxidation states make the atoms behave. So what we do is we do a mental correlation. We can always predict this number. This number is not always accurate, but this number gives us a fixed reference point. It's like, you have some reference point. And then you memorize, okay, that reference point is, like say you're looking at distant mountains, and you memorize that. Okay, that reference point is this tall. And then you can compare other things to that, right? It's not that, it's 100% accurate. It just gives us a way of comparing things. And so this turns out to be extremely powerful and useful tool. Well, what formal charge is, did anybody figure out what formal charge is? Based on this equation, what does formal charge translate to? When you look at this equation, do you see it? Does the equation talk to you and say, formal charge is the charge, let's see, formal charge is the charge on the atom. Can you say it in words? Is the charge on the atom formal charge is the charge on the atom making the opposite assumption. So formal charge is the charge assuming the bond is 100% not ionic, but 100%. What's the opposite of ionic? Would be covalent. Well, are all bonds 100% covalent? Certainly not, but this gives us the two extremes. So now we have it covered from one extreme to the other. It can't go outside this range. And so the charge has got to be somewhere in between the two extremes, right? And there we can kind of figure it out. But formal charge helps us in also making comparisons, and so the formal charge is going to be the charge. So what we're missing there is the formal charge. So let's go back and look at this Lewis structure here, and then look at the formal charge. If we assume that the bond is 100% covalent, then it's a 50-50 split down the middle. So it's equal sharing. We just divide up the electrons differently. And then just count them. The 2, 4, 6. How many valence electrons is oxygen supposed to have? 6. It has 6. So the formal charge is 0. We circle the formal charges, or I circle them, but they're typically circled. Nitrogen, 2, 4. Nitrogen is supposed to have 5, so this is plus. Oxygen, 6, so it's 0. And so nitrogen has a positive formal charge. Usually we just write the positive formal charge. Do you see it's circled here? And the formal charge of nitrogen is +1, oxygen is 0. We don't show the zeros, it just takes up too much space. And so the net charge is the sum of the formal charges. 0 plus 1 plus 0 is +1. That's it. And not only is this the parent, this is the actual charge on that nitrogen, because the nitrogen is actually missing an electron. So in this case, that's the actual charge. And so formal charge is the opposite assumption. So both tools. And so we never want to compare formal charge with oxidation state, because oxidation, what's the oxidation state of nitrogen? The oxidation state on nitrogen is +5. And so at one extreme, if we assume the bond is 100% ionic, we get a +5 charge on nitrogen. It would look like this. If this were 100% ionic, I better draw the Lewis structure like this. I better draw the Lewis structure like this, because winner take all. Right? This ionic bonding is winner take all. If this were covalent, I'd draw it like this, where there's sharing. This is more covalent than it is ionic, so we use this structure. We don't show it like this. But is it 100% covalent? No, it's not 100% covalent. These are what we call polar. Although nitrogen and oxygen have close electronegativities, this is more nonpolar than it is polar. So the charge is going to be closer to this. So the charge is between +1 on nitrogen to +5, depending on how ionic it is. The higher the percent ionic character, the higher the charge is going to be. And so this just shows us the two extremes of charge. The charge on oxygen is going to be between 0 and -2. Well, we don't know what that charge is. It's not +1 and it's not +5. What is the charge on nitrogen? Well, in this case, the charge is actually +1 because we end up with that as the formal charge on there. But oxygen, the charge is between 0 and -2. So typically what we do with oxygen is we don't know it, so we just guesstimate it. Well, we don't really guesstimate it. We just call it delta minus. Delta minus is just some charge on oxygen, whatever that is. We can figure out those charges using theory, quantum mechanics, or other stuff. The formal charge turns out to be a pretty powerful tool for analyzing Lewis structures, and also for predicting acid-base properties as well. And so what we could have done here is we could have done this. We could have done a triple and a single. If we did a triple and a single, it would have come out the same. Everybody would have an octet. Net charge would be the same. But when we look at the formal charges here, this oxygen comes out as positive, and this oxygen comes out as negative. And so what that means is this oxygen lost an electron, this oxygen gained an electron. Is that a stable situation? No, this is not a stable, because if you had a tug-of-war between two oxygens, and the oxygens have the same electronegativity, is one going to win and the other is going to lose? No, you wouldn't expect it. And so this is what we call an unstable formal charge. Whenever we have formal charges, we try to minimize those because taking electrons away costs energy. Here, this is much better because this is 0 and 0. And so one of these didn't lose, the other gained. Well, formal charge is going to turn out to be critical for figuring out what proper Lewis structures are. And so usually we want the negative formal charges on the most electronegative elements. You should try to keep the formal charges as small as possible. And the formal charge of the same size on adjacent atoms is unlikely. Look at this, positive and positive. Is that a favorable situation there? No, they're going to repel each other, those two atoms. So it's going to weaken the bond tremendously. So that's not good either. All right, then we go on to resonance. Sometimes we have a choice on the bonds. For example, what we could have over here is a double bond on the left, or we could have a double bond on the right. But you say those are the two same structures. Yeah, they are the exact same structure, but the thing is we see how the electron cloud can be distributed. And so what we do is we fix the atoms in position. If we fix the atoms in position, this would be ozone here. If we fix the atoms in position, then there are different ways of arranging the electrons. We do not ever move the atoms. We just move the electrons. So this is what these arrows are showing. So for example, we can convert from one resonance form to the other by, let's take this lone pair and put them in the bond, and then take this bonding pair and put it as a lone pair. And when we do that, it converts to this resonance form. Well, we can convert it back to this resonance form by taking the lone pair, putting it in the bond, and taking this bonding pair out. And so these two. And so a lot of people think resonance form, we're just going to have these electrons just shifting back and forth, so it just resonates from one structure to the other structure. But it turns out that this is just a failure of Lewis structures. It turns out neither of these is correct, because when we look at the actual electron cloud distribution in ozone, it's pretty even. One side doesn't have more electron cloud or density than the other, and it's not flipping back and forth. This is it, static over time. And so one way of thinking about that is like this. This is called the resonance hybrid here. In the resonance hybrid, we don't have a negative going from here to here and back and forth. What we have is we have a negative 1/2 and a negative 1/2. And then we don't have a double and a single and a double. What we have is a 1.5 bond and a 1.5 bond. And so the way of thinking about this resonance form for ozone is like this. It's like water. You know, the electron cloud's like water or fog. It's just going to spread out, and it's going to spread out as far apart as possible. And so if we have this, let's say I have a tub of water. This is like 2 feet of water, and this is 1 foot of water. This is fine if there's some wall that blocks it. If there's some wall that blocks it, then on the left I could have 2 feet of water, and on the right I could have just 1 foot of water. It's no problem. But when we look at that, is there a wall that blocks the electron cloud from shifting from one side to the other? It turns out no, this is called a mechanism. This mechanism shows that there's no barrier, there's no wall that blocks it. And so what we do is, if we remove this wall here, then can we sustain 2 feet of water on the left and 1 foot? No, what's going to happen is, the electron cloud is going to spread out over both. And so rather than 2 feet and 1 foot here, we're going to get 1.5 feet here and 1.5 feet here. This is called bond order. The bond order was 2 and 1, but now it's going to be a 1.5 and a 1.5, which means a 1.5 bond. Well, what's a 1.5 bond? 1.5 bond is just how much electron cloud density you have between the atoms. That's it. And the same thing with the lone pair density. That's going to spread out over both oxygen. So it's just going to be like water and just even out over the whole thing. So you can go. We have exceptions to the octet rule. Would be like this. I forgot to show these. These are called free radicals. Free radicals, they have a lone electron. The lone electron is called a dangling bond because this wants to bond to something. So this is called a methyl radical. This is called a hydroxyl radical. This is a nitrosyl radical. These radicals are, highly reactive. And so this is also possible. The formal charge, what's the formal charge on this oxygen here? Zero. The formal charge on the carbon? Zero. And the formal charge on the nitrogen? It's also zero. And so these all have zero formal charges. Even though they have zero formal charges, it's still very reactive because they don't have an octet. And we want an octet to complete that shell. Some things are going to have incomplete octets, even though we can complete the octet. So, for example, here, boron, that has 2, 4, 6 electrons total around it. That's less than an octet. All we have to do is form a double bond here. If we form a double bond, then we get an octet around everything. The only thing is, here, there are no formal charges here. But when we go here, if we form a double bond, we can put a positive formal charge on fluorine, and we should have circled this, a negative formal charge on boron. Well, that means if there's a tug-of-war between fluorine and boron, who won that tug-of-war? Fluorine versus boron, who won the tug-of-war for the electron? Boron. Does it make sense that boron's stronger than fluorine? More powerful oxidizer than fluorine? Does that make any sense at all? No, it doesn't. And so these don't happen. This is not going to happen. This is showing it. So, in other words, boron is going to be stuck here with less than fluorine will never form a double bond. So this doesn't happen. What's this showing here? See what that's showing? Yeah. This is showing this. Rather than showing this bond as a covalent bond, this is showing the bond as a ionic bond. Well, when do we show it as an ionic bond? When do we show it as a covalent bond? Well, it depends on the... what does it depend on? Well, if it's a metal and a nonmetal, we're going to show it as an ionic bond. Well, these are two nonmetals. So should we show it as an ionic bond or should we show it as a covalent bond? Well, typically we show it as a covalent, but why are they showing it as ionic? Well, it could be due to the electronegativity difference between fluorine and boron. Maybe this is quite ionic in character. So let's just take a look at fluorine and boron really quick and then see. Fluorine is a 4O, boron is a 2O. And so the difference in electronegativity between fluorine and boron is 2. If the difference in electronegativity is 2, should we represent that bond as an ionic bond or should we represent that bond as a covalent bond? Well, if the difference in electronegativity is 2, you know, the trend shows that it's about this, 60 whatever percent ionic. And so it's creeping up towards more ionic, although HF breaks that trend. So maybe BF3 is around here. We don't know because we didn't do the actual calculation. We're just guessing. It could be. And so it's borderline, right? Borderline means, well, maybe we could show it as ionic, maybe we could show it as covalent. And so this is something you wouldn't have done. And in fact, this is just kind of weird because this structure is out. And so this is the same structure. These two structures are the same, except this one's showing it as a covalent bond, this one's showing it as a ionic bond. So it's somewhere in between these. Now, why is it showing this as 1 ionic and 2 covalents? Why not just show all 3 as ionic? You could do that as well. If you show all 3 as ionic, what would the charge on boron be? +3, and all the fluorines would be -1. Do that as well. So for right now, just ignore. This structure will ignore. This structure we can't do. We can't double bond fluorine. And so this is left without an octet. Well, that's going to change its reactivity. Boron, BF3, this is highly reactive because it has less than an octet. There's one way of getting an octet here, and that is if we react this with a Lewis base. What's a Lewis base? A Lewis base is a electron pair donor. A Lewis acid is a electron pair acceptor. So BF3 is a powerful Lewis acid. It's a powerful Lewis acid because it can easily accept an electron pair from a Lewis base. This would be a Lewis base, fluoride. It has a lone pair it can donate. And so if it donates there, we form BF4 plus. Excuse me, not plus, BF4 minus. Where boron now has a negative formal charge, the fluorines all have 0 formal charge. And so that takes care of the octet. So that's just to make the octet. All right, this shows an octet here, but the PCl3 is going to have 1 lone pair. PCl5 also exists. Actually, this is very stable. So this is PCl5 with what we call an expanded octet. When can we have an expanded octet? When we can have expanded octets, or here, we will never see an expanded octet in the second period. From the third period on, we can have expanded octets. And so nitrogen would never do this. But phosphorus can do this. And we can form PCl5 like this. Formal charge is all 0. SF6, this is a very stable molecule. This is expanded octet. This is very stable here. And so we can have expanded octets. This is sulfate. Sulfate, if we just do it using octets, then we end up with formal charges. The formal charges on each of the oxygens are -1. The formal charge on sulfur is +2. However, if we expand the octet, that is, if we form 2 double bonds here, we can drop the formal charges. So these terminal oxygens here would have -1. These oxygens would have 0. This whole thing. So the advantage of expanding the octet is to reduce the formal charge. Sulfur can potentially expand the octet. It turns out there are resonance forms for this. Because, we could have a top and bottom. We could have top right. We could have top left. We could have bottom left and bottom right. And so there are a whole bunch of ways we can arrange the double bonds there. And so those would be all resonance forms for sulfate. Here. We'll expand it octet. We'll come back to sulfate. Now, can you write all the resonance forms for sulfate? And then tell me what the hybrid would look like. So let's just start. This one has double bond top, bottom. Another resonance form would be double bond top, left. How many different combinations are there? 4? Okay, write them all out and let's see. And then we'll complete it. We got to do the oxygens and then determine all the formal charges. When we do resonance forms, we use a double-headed arrow to indicate resonance.